Hello and welcome back. In this video, we're going to be talking about image processing in a very particular application in medical imaging. And this is image processing for virus understanding, and in particular, to understand the shape of the HIV virus. This actually brings a lot of challenges, as we are going to see. We're going to have to talk about many topics in image processing, including image acquisition. And let's start with that. There are many ways to acquire images. And before we do that, we have to understand one of the basic things is the size of the structure that we're trying to acquire. And here we see a scale of very different structures. And depending on what is that we want to acquire, what type of technology we're going to be using to acquire that data. And of course, we're used to light. We're used to cameras, basically light reflecting from objects and then giving us a picture. But depending on the size of the objects and their scale, we might need different modalities for image acquisition. During this video, we are interested in viruses. And then we're going to be talking about nanometers or Armstrong scales. And in particular, what we're going to use is not light, we're going to use electrons to acquire our image, because we are at a very small scale. Again, in the orders of nanometers and Armstrongs. Now, let me just tell you why we are interested in something very small in the HIV virus. And I hope this diagram, although a bit complicated, I think it illustrates a lot of the challenges that we are going to have and why is this so important, what I'm going to explain next. So here we have an HIV virus. Remember, we're talking again, maybe 100 Armstrong, just very small structures. And here, basically, we have the host cell. So basically, the virus is trying to latch into this host. And in order to do that, it uses things here which are called envelope or spikes. And then they go and try to latch here, as is shown in this diagram. And then basically transmission goes into the host cell. So we are interested in this virus, and in particular, and this might surprise you, and it will surprise you even more when you see the images, we are interested in this. Basically in these envelopes or spikes. They're called envelopes and often they're just written as ENV. Once again, because that's what the HIV is using to latch itself into the membrane of the host cell. And if we understand that structure, we might be able to stop and to block that connection and hopefully stop transmission. That's what we want to get. Now we are at those small scales, remember. And then what we need to use is not light. We won't be able with light to get to that scale. We use electrons. And here is a diagram. Now, once again, you are used to basically light. So light comes, reflects in objects like me, and then regular cameras, like the video camera that is recording right now, captures the reflection. In transmission electron microscopy, basically we have the specimen. We basically have a specimen with HIV, for example, but other specimens are possible as well. Microscopy is used all over for biological research. Electrons basically go, it's like you throw electrons into the specimen, and you see, and you let them just go through. Basically, you capture the image. You capture the image of the specimen by measuring how the electrons go through. And we see that in this diagram. There is a lens, and there is the image plane. That's where things basically get captured. This is a picture of this device. The high-end devices are not very cheap. They can cost millions of dollars. So this is not something that you carry one with you like a regular digital camera. once again, the issue is electrons are hitting the specimen basically, and then they go through and we capture them. So for us, it's a different way of creating images, but the important way is that we can create images for these particles that are very, 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 very small. So that's electron microscopy. And here is an image of what you will get from electron microscopy. Now remember, have always in mind, this is what we saw in the previous diagram. This is what we are looking for. One projection of that. So you took this electron microscopy and you basically threw electrons and you have one projection of that, and that's basically what you have here. So this is this. Doesn't look very nice, but we're going to have to deal with that. And we're actually going to change the modality a little bit. But it's not that it doesn't look very nice because the instrument is not very good or the person that was taking the image is not very good in doing that. This is actually extremely good quality for this technology. And we need this technology because we want to get these very tiny, very, very tiny elements. So we're going to have to deal with this. Before I do that, before I show you how to do that, this is the beauty of image processing, that we're going to be able to deal with this. Let me just talk a bit more about tomography. Instead of just putting the specimen and just taking one view, what you do in tomography is you rotate the specimen. So let me just show you this here. So you have the specimen, and then you rotate it, and you rotate it, and you take multiple images of this rotation, and that's what's called tomography. Now, what do I mean by cryo? Okay, first of all, we now know what's electron. Instead of electron microscopy, we say electron tomography because we have multiple projections. Cryo is because with the specimen, before we put here, we freeze it at cryo temperatures. Now, this technology helps to reduce radiation. This is very important. When light is hitting me, you can take as many pictures as you want of me. I'm not going to get hurt by that. When you throw electrons at a specimen, you're hurting the specimen. You're changing it. So you're changing the shape of what you're trying to understand the shape of. And this is very dangerous. So this technique of cryo electron tomography helps to reduce the radiation of that, and also helps you to obtain three-dimensional information because you have multiple tilts. So that's basically what we do. And let's see images in a second, but we are doing cryo electron tomography. This is just one of those images. Again, remember, we are interested in this kind of stuff. And actually, we are interested in these spikes. You might be able to see some of them there. But that's what we want to get, the three-dimensional shape of that. They're very, very tiny, and as we see, very, very noisy. So here's where you get the call to image processing. And just to say once again what kind of data we have, we got tilts. Basically, we had the specimen, we rotate, we throw the electrons at it, we get one projection. We do a different rotation, we get a different projection. A different rotation, a different projection. Then we put them together and we get the three dimensions. So I'm going to always show you slices of this because most of the time I'm going to show you 3D when we get the reconstruction. But remember, this is supposed to represent this. And we obtain it. So here was the specimen, very, very tiny. And here is the image in the computer. Now, the image processing starts with putting all these projections together to get the 3D. Normally, although there are alternatives, that's done with what's called fiducials. So you basically embed in the specimen gold particles, and then you have a gold particle, let's say this pink, and then you know where the gold particle is in every single of the projections, and then you align the images based on those gold particles. So you throw a few and then you put them together, and that helps you to stack the images and to basically get the 3D in the computer of the real three-dimensional virus. Now, there is one thing that I want to explain here. When you're doing the projection, you can see this is very thin. So I'm illustrating it much wider. We're talking about very, very thin. So you do cryotomography or cryomicroscopy, you have a very thin slice at cryo temperatures. So if I do the projection that I'm going to try to throw electrons from here, you're not going to get a lot because it's very, very thin. So look at my hand now. It's okay to have electrons going like this, but not going like this. Okay? So if I have something very, very thin, I can just do this. Remember, rotating the specimen is like rotating the rays. So I can have rays here, but not rays here, and maybe also not rays there. So we actually don't have the full 180 degrees. We normally, out of the 180 degrees, we might basically miss here 30 degrees and another 30 degrees there. And that's called a missing wedge. So as we're going to see, yet another problem. We actually don't have all the data we wanted to have because of this missing wedge. But now we're about to get into the image processing. We acquire the data, we align the projections using gold particles most of the time, and now it's time to find those viruses and find those envelopes. Now, this is what you see. You have a line, and this is what you see. Remember, this is the schematic of what we're looking for. But these are slices of this 3D that we just have done. Now, do you see here the envelopes or the spikes? No, you don't see them. This is where we need image processing. We have extremely noisy data. We have the missing wedge. We have tons of problems. Are we going to be able to reconstruct this 3D? I'm going to show you that yes, the answer is yes, up to certain accuracy, of course. Again, these are just slices on the 3D volume that was reconstructed with cryotomography. This is what we have. This is the process that we have. We had basically a virus or a structure inside a specimen. We took multiple projections. Look how I represented here the missing wedge. We didn't take the whole around projections. We basically have missing wedge here. So we took that and we kind of get a noisy version in this 3D volume. But there is one thing which is very important. We get multiple copies of this. As we have seen, let me show you that again. We might have multiple copies. You see one, you see another one coming here. I'm going to show you more. We have multiple copies of this, and we also have multiple copies of this. And that's what we are going to exploit with image processing. We are going to exploit that we have not one very noisy example, but multiple very noisy examples. So hopefully we can extract them, put them together, and get the 3 dimensions that we want. Remember one thing. When we talk about image denoising, we already discussed that if you have multiple copies of the same object with random noise added, one of the best things you can do for denoising is add all those multiple copies. If the noise has zero mean and is random, then it will just cancel each other. That basically was the concept behind non-local means. It's also the concept behind just local averaging. You basically want to average things that are repetitions of the same, and that will help you to eliminate the noise. Remember, if you average 10, the variance of the noise goes down by the square of that, so 100. The more you average, the more you manage to denoise. So that's great, but what's the challenge here? Multiple challenges. These images are very noisy. the spikes, the envelopes here, are rotated. We have to align them before we average them. Otherwise, it will be a mess, okay? If you average this with this, let's say these two vectors, you get something like this. Nothing to do with any of them. So you have to first align them, and I'm going to illustrate that in one of the next slides. So you have to align them. And also, are they identical copies? Maybe there are multiple different structures, maybe slightly different, but still different. So we're going to have to rotate, align them, group only those that are the same, and only after we do all that, then we're allowed to average. So here is the problem. Let me illustrate that to you. Let's say that we have 3 scenes, as we see here. 1, 2, 3. Now let's simulate cryo-electron tomography for this. We basically get multiple copies of each one. That's a good part. We get multiple copies of each one. Very noisy. Okay? That's not so good. The multiple copies is good, the noise is not very good, but we have to deal with that. We get them rotated. That's also not very good, but we're going to have to deal with that. And then we get the missing wedge. Okay? So, and of course, we don't have the originals. This is what we have. So, somebody gave you this. Very noisy data with missing data, the missing wedge. Didn't give you in the columns. They're all unorganized. So you have to be able, from them, you have to be able to group the ones that came from basically the same building. Here, we have to be able to group back. Here, you have to rotate back, and all that from this noisy data with a lot of missing information. If we have 30 degrees missing, we have 60 degrees missing out of 180. That's a lot of missing information, and that's represented here. So this holds is a realistic proportion. You have this, group, align, do everything, and hopefully after you're done, of course, you're doing all the rotations, all the groupings and everything together. Hopefully you're able to reconstruct back the virus or the images as we represent here. So imagine that you take multiple cameras of the same scene, but you occlude the cameras in a random fashion. You add a lot of noise, so now you have multiple pictures of the same scene, and now somebody comes and say, hey, give me back the shape of that building. Very challenging, but hopefully doable because you have multiple copies. So what are some of the challenges that we have here? We have very low SNR, we have this problem with alignments and missing data, and we need a lot of data to remove the noise, and basically we are going to have computational challenges. So let's see how we address each one of these challenges, in part together, in part separate. And this is a very tough problem, but I think you're going to get happy to see the kind of results that we can get. So let's get into that. The first thing we have to do is define a distance. Remember, we want to align these projections or these three-dimensional shapes, but with missing information, with the missing wedge and with noise. So how do I design, going back to the images in 2D projections of the buildings, how do I design when these two are aligned or they are not aligned? I need to basically define a distance. And we take any two images, we look at two projections or two 3 dimensions, depending where are we working, and how do I know if these two are aligned or not? That's the first thing we need to do, basically to define a distance. We are going to allow the images to rotate and also translate later on, and we want to be able to say, hey, keep rotating, stop. That's where you're aligned. So I need to define that distance between two images with robustness to noise and with the missing wedge. So let's illustrate that. That's the first step every time that we need to align images. How do I decide when they are already aligned? So we have one image here, which I represent as a one-dimensional signal. Here we have this one-dimensional signal, and we represent it here. But we don't have the whole signal. We actually have the missing wedge. So we only have the signal in certain parts of it. Now we have another signal, and also for it, we have the missing wedge. Very important. We basically don't have the missing wedge in the same place. Remember, these particles were rotated. So the missing wedge is kind of fixed for a particular acquisition, but the particles are all rotated. So with respect to them, the missing wedge is all the time in a different position. Now you actually know where the missing wedge is, or you can guess it. Either you know from the instrument, or you kind of guess it because there is a lack of signal to noise there. And these are basically the two images that we need to basically decide a distance between them. We wish to have them like here, complete, but we only have portions of them. And the only place where we can compare them is when we have portions of both. So here we had information for the first one, but there is no information for the second one. Here we had for the second one, no for the first one. So the only place where we can compare is when we have information for both of them. So we can take a distance, Euclidean distance or any distance that you think is appropriate, but we need to only consider places where both of them are available, and that's represented by this product. So this and this are basically square binary signals. 1, I have a signal, 0, I don't have a signal, and I can only look at places where both of them are 1, so I have signals for both of them. And again, you can just take that basically almost any type of metric that you wish, and illustrating here with just Euclidean type of distances. And this is going to be kind of your distance. You take the difference between the images, but you only consider where both of them are available. And of course, you have to normalize by the amount of energy that you have per signal. And that's basically written here. That's standard. Otherwise, this distance will depend on how much overlap you found, and we need to basically normalize for that. So that's the distance that we are going to use to illustrate the examples in the next few slides. Now, this distance actually is not too hard to compute. You can actually compute in the Fourier domain. We haven't discussed in this course too much about Fourier. For those that have a background in signal processing, you know what Fourier is, but we did talk about DCT, the discrete cosine transform. So basically, you take the signals, go into a different domain in the Fourier domain, and in that domain, you do this calculation. It's very convenient to do that for computational reasons. It's also very convenient to do that there because it's very easy to represent the wedge, the missing information there. So we have this distance, which is a Euclidean distance, but weighted for the regions where we have common information.